We're going to look at, in this next section, what are called parent functions. And parent functions are all of the major different types of function that we might see. So we're going to look at absolute value, parabolas, square root function, cubic function, and logarithmic functions. And that's in addition to what you might think of a pretty standard function like a line. So whenever you see an absolute value equation, it's going to usually look something like y equals absolute value of x, and x is going to be trapped inside those bars. That's the basic parent function, and then from there we can do any modifications. So if we were to graph that, we might start with, let's say, a t-chart where we insert x and y, and we're always going to want to start these parent functions around 0. So let's do -2, -1, 0, 1, and 2. We know the absolute value. If we were to plug in -2 here, absolute value of that is just a +2. And then absolute value of -1, +1, and so forth. So when you go to draw your graph, it's going to end up forming a V shape, and that's how you can recognize this. So if you go back 2, you go up 2, you go back 1, you go up 1, 0, 0, 1, 1, 2, 2. And you end up with this perfectly straight V-shaped graph. That's what the absolute value graph looks like. Now the part that we're going to get into more in this section is being able to move that graph or modify that graph. For example, what would it take to make the graph become upside down? Or what would it take to shift the graph over 2 units to the right? Or shift it up 1 unit? Or do any combination of these, shift it over, shift it up, and flip it upside down. So those are all things that you can do when you're modifying the parent function. We're going to start with a quick example on this one, and we'll save the rest for later. But whenever you modify something directly next to x, so if we were to write the function y is equal to the absolute value of x minus 1, what that would do is that would shift the graph over in the x direction, so left and right, in the opposite way you expect. So minus I would generally think of as going left. It actually is going to shift it 1 unit to the right. So the same graph right here shifted 1 over to the right when you put that -1 directly next to the x, either in parentheses or in this case in the absolute value bars. When you go back to the original function and you add 1 to the outside of the parentheses, or outside in this case of the absolute value bars, it's going to take your original purple graph and move it up 1 unit. So you'd be looking at a graph that looks something like this, where you start exactly 1 unit up from where you started by doing that +1. And the y, when you're modifying the y, it moves in the direction you expect. Plus is going to move it up. And then finally, if you wanted to take that original function and put a negative out front of the absolute value bars, or out front of the parentheses, it's going to flip the graph upside down. So your original purple graph is going to now look something like this, where it is flipped upside down. So before we get too far into the details, let's look at the other parent functions and their basic shapes, and then we'll figure out how to modify all of them. Now a parabola, that's our standard U-shaped graph. It's the equation y equals x squared, and then any modifications you do from there. If you were to make yourself a t-chart, you have x and y. Plug in some common values here, and if you were to take -2 and you were to square it, it would become +4. -1 squared would be +1, 0 is 0, 1 is 1, 2 is 4. And so similar to the absolute value graph, everything stays positive here, except this time, instead of a strict V shape, we end up getting something that is going to be curved and U-shaped. And you can see we can plot all of our points here, And if we're going to graph that, it should have a more gentle curve to it. Same rules apply. If we're moving it, we can put a plus, let's say we did a -1, we did y equals x minus 1 whole quantity squared, just like above. That's going to move the whole graph 1 unit to the right. Like I said, we'll get into the details of all that later. The square root function. This one is going to be the y equals the square root of x. So whatever x is, you take the square root of it and then you get y. So essentially you're forming a sideways parabola, except that we're only going to look at the positive part of it. So if I were to make my t-chart over here, my x and y, I'm actually going to do something interesting. I'm going to plug in no negative values in here. And the reason is, if I were to plug in, let's say, a -2, the square root of -2 is actually undefined. It is a non-real number. Plug it in your calculator, it's going to give you an error. You can't take the square root of a negative. So we cannot do negative numbers. But if we start at 0, square root of 0 is 0. Square root of 1 is 1. If we plugged in 2 here, the square root of 2 is going to come out to some sort of ugly decimal. So I'm actually going to skip all the way to 4. The square root of 4 is 2. And then skip down to 9, and the square root of 9 is 3. So in making the square root graph, we actually tend to skip our x's if we're trying to not get a bunch of decimals. And when we go to draw our graph, we're going to find that this graph is going to level out very quickly. So we start at 0, 0, and nothing goes in the negative, so that's the very first point on the graph. We go to 1, 1. We have to go over 4 before we get up to 2. We have to go over 9 before we get up to 3. And you end up with something like that. So that gently increasing graph is going to be your square root graph. And you can see how it looks like a parabola on its side cut in half. A cubic function. So if you think of our parabola being y equals x squared, a cubic function is y equals x to the third power, or x cubed. If we make a quick t-chart here, we can go back to our normal use of negative numbers, which is just fine. And you take -2 to the third power. -2 times -2 is +4, times -2 one more time is going to be -8. So negative numbers result in negative x's result in negative y's. -1 times -1 is +1, times -1 is -1. 0 times 0 times 0 is 0, 1 times 1 times 1 is 1, and 2 times 2 times 2 is +8. So we can go ahead and create our axes here. And what we're going to find is that this graph is going to be a very rapidly increasing and decreasing graph. And it's going to be known by its S shape. So if we go back to down 8, get our first point, 1, -1 and 1, 0 and 0, 1 and 1, 2 and 8, you end up getting a graph that very quickly comes up, levels out around the middle, and then quickly goes up. So it has this swervy curve to it, kind of like an S. Last one we're going to look at, more unusual function that we don't have as much experience with, is the logarithmic function. Log functions are interesting in that they work on the idea of multipliers of x. It basically counts how many decimal places you're going to, how many zeros are in that function. So if we were to make an XY chart here and start plugging things into our calculator to see what it gives us for a log, if we plugged in the log of 0, you can't take the log of negatives, and if you actually even typed in the log of 0, your calculator would give you an error. So it cannot do that. So it has to be something slightly greater than 0. If you were to type in the log of 1/10, the log of 1/10 would be -1. If you on your calculator typed in the log of 1, you're going to get 0. Log of 10, you're going to get 1. Log of 100, you're going to get 2. If you typed in 1,000, you'd get 3. Basically how this works here is if you were to rewrite these numbers as 10 to some power, so 10 to the -1 power, 10 to the 0 power, 10 to the 1 power, which is 10, 10 to the second power, 10 squared, which is 100, and so forth, the power is what y will become. So the log function figures out what is the power that 10 is being applied to. If we were to draw a graph of that, then what we would find is that nothing is going to be over here in the negative x's, and in fact we will never even cross the y-axis. So the y-axis, it will get closer and closer to it forever, but it will never touch it. As we move on our x's, we'd have x equals 1, and then farther out you'd get to 10, and much farther out you get to 100, and so forth. And so the spacing on here is a little bit harder to write, but if we were to mark out our y-axis here, -1, 0, 1, and 2, we know that we would have a point at 1, 1, or excuse me, at 1, 0. Right, look at our chart here, we have a point at 1, 0. We know that if we go very, very close to the y-axis, when x equals 1/10, we can get a point down at -1. So right around there. Out at 10, we get a point here at y equals 1, and then way out at 100, we would get a point at y equals 2. And so we see something like this happening, where that goes down forever really close to the axis, and this very slowly goes up forever. And that is our logarithmic function. So these are our different parent functions. If you recognize any of these basic shapes, we can modify them. We can move them to the left, to the right, up, down, and flip them upside down using our different transformations.